Hi class, so this is the introduction to chapter 17. Now this is just an introduction, and the idea behind this is mostly just to make sure that you are able to access these videos and able to watch them. So I'm not going to get very far in this at all. There are the full lecture videos already on Blackboard for you. So again, this is mostly a test for this first semester as we transition to a 100% online class. So you should be seeing the screen now with the chapter 17 logo. So this is from the PowerPoints that are also available for you. So when I move through here, I can write on the screen, I can erase in the screen just like I can on the board in our classroom. So there you go. Going on to the next slide, these are the sections we'll be covering in chapter 17. So in chapter 16, we covered acid-base solubility, or acid bases, and we started introducing the idea of using equilibrium and ice tables in them when we were finding the pH of a weak acid, a weak base, a polyprotic acid, and for the salt solutions that contained the conjugate of a weak acid or weak base. So we're going to introduce the idea of the common ion effect, go into buffers, acid-base titrations. So this is going to be finding the pH at a different point during a titration. So at the beginning, halfway through, that kind of stuff. Solubility equilibria. So this is going back to the chapter 4, the table of solubility, and looking at things that are generally not very soluble but are soluble to a small amount, and using the idea of equilibrium and ice tables to determine exactly what their solubility is. What kind of factors can affect solubility, such as pH, temperature, that kind of thing, and then how to use a difference in solubility to separate out ions in a precipitation reaction. So the idea of a common ion effect is that I have some sort of, and we're going to focus on weak acids at first, I have some sort of a weak acid in solution. So we're going to start with our famous weak acid, which is acetic acid. So reacting with water to make the acetate ion and the hydronium ion. So you should now see the ice table down here. So in a normal, if I was just asking you to find the pH of this solution, I have 1 liter of solution that has 0.1 moles, so that is 0.1 molar. 0.1 mole divided by 1 liter, 0.1 molar. So remember, in ice tables, these always have to be in molarity. And you would use the ice table to determine what the concentration of the hydronium is at equilibrium, solve for X, and take the negative log of that to find pH. So here would be our pH of a 0.1 mole solution, 1 molar solution of acetic acid, using what we know in chapter 3. Now, this is an equilibrium reaction. The arrows go both ways. So in Le Chatelier's principle, back from chapter 15, we learned that we can mess up this equilibrium by adding or removing a reactant or product. So if we look over here, this is the acetate ion, and in chapter 16 we learned that salt solutions often contain the conjugates of weak acids or weak bases. So sodium acetate contains the acetate ion. So if I added sodium acetate would be adding the acetate ion, which would increase the concentration of a product. According to Le Chatelier, that would drive the reaction back this way. But it also depends on how much I add. In other words, here I would not be starting at 0. I can't initially drive the reaction backwards because I don't have any hydronium. So we're going to have to apply this a little bit differently. I'm starting with some amount of the acetate ion here. So this is called the common ion effect, where I start with 2 different things in solution, in this case acetic acid and sodium acetate, that have a common ion. Both of them have the common ion of acetate. You can also do this with bases. So let's look at an example of this. Determine the pH of a solution prepared by adding 0.050 moles of sodium acetate to 1 liter of 0.1 molar acetic acid assuming that the addition of sodium acetate does not change the volume of solution. So first of all, this is going to require an ice table to solve, and ice tables have to be in molarities. Now, luckily, because I am 1 molar right here, or I'm 1 liter right here, then I can use this as a molarity as well, because again, molarity is moles per liter. In this case, I'm just dividing by 1 liter. So 0.1 molar sodium acetate, or 0.05 molar of sodium acetate. Now, sodium, we learned, does not affect the pH. It's the conjugate of a strong base. So we're just going to ignore that and really just focus on the acetate ion, because that's the one that's the common anyways. There is no sodium in acetic acid. So I'm really just looking at the acetic acid and the acetate ion. So let's go ahead and write out our equilibrium reaction. So we have our acetic acid. We react it with water. So notice I'm not reacting it with the acetate ion, because these are not reacting with each other. They just happen to be in the same equilibrium reaction. And then I have my hydronium ion and my acetate ion. Wow, I'm getting the horizontal things just like I do in any other board. CH3. Okay. So now that we have our reaction, let's make our ice table. So acetic acid, I'm starting with 0.1 molar, so 0.10 molar here. Again, we ignore water, it's pure liquid. Excuse me. And then hydronium here, we're starting with nothing. But the acetate is not starting with 0, it's starting with 0.050 molar. And again, because I have no hydronium here, I know the reaction has to run forward because I have 0. I cannot run it backwards, which means this is going to be minus x plus x plus x, just like it was for chapter 16. But now 0.050 plus x. And then 0.10 molar minus x. So now that we have our ice table, we can set this up in our equilibrium expression. So Ka is equal to products over reactants. So my products are hydronium and acetate. So hydronium was X, and then the acetate ion was 0.050 plus X. And on the bottom, my acetic acid was 0.10 minus X. And this is going to be equal to the Ka of acetic acid, not the Ka of acetate, because the reaction is running forward, so we're using the Ka of our reactant, which is acetic acid. So from the table of weak acids, we would find that the Ka for acetic acid is 1.8 times 10 to the negative fifth. And at this point, we would solve for X. And hopefully, we will be able to assume X is small, so that we don't have to do the quadratic. So if we assume X is small, remember you ignore anywhere where X is added or subtracted, but not where it is being multiplied. So if I assume X is small, then I can ignore the plus X and the minus X, but I cannot ignore where it's being multiplied. So this would now become 0.050 times X on the top, and on the bottom just 0.10, and you can go ahead and solve it. So I'm going to go ahead for the speed of this and solve that, again assuming that X is small. We get X is 3.6 times 10 to the negative fifth. Since that is my concentration of hydronium ion, negative log of that will be pH. So here is my pH, 4.44. Now remember, we were starting with 0.1 molar acetic acid, and earlier we used an ice table to find that the pH of 0.1 molar acetic acid is 2.87, which is acidic, less than 7. By adding acetate, sodium acetate, which contains a conjugate base, that should increase our pH. And sure enough, it did increase it. Our pH went up to 4.44. So it shifted the equilibrium back. So because it shifted the equilibrium back, it decreased the amount of hydronium. Decreasing the amount of hydronium will raise the pH. So that is the general idea behind common ion effect. And then the next lesson will go into how we use this for buffers. All right, so to confirm that you actually watched this video, the key word of the day is ELSA. So I hope everybody had a good time, and hopefully this will work out in the weeks to come.